Prova. tranquillo. Sì, anche ieri lo facevo.
Effettivamente adesso non fa più. Dimmi tu quando, eh?
No?
Dimmi tu quando.
Sì, appena parte il video di là.
Ok.
Sbagliato come soluzione, dici? Che vuol dire sbagliato?
Dobbiamo riavviare la tirata. Vediamo se lui
Okay, good morning everyone. Sorry for the little delay of issues. It's a pleasure to introduce you this morning Annalisa Barla, who's giving this talk on Python in medicine, signal processing, learning and visualization of temporal data. So big applause to her. Thank you.
Hi everyone, good morning. I'm Annalisa Barla and it's a great pleasure to be here. I am a professor in computer science at the University of Genova, and I'm going to try to discuss a little bit on what we do in my research group on machine learning data analysis, especially on biomedical data. And I'm going to try to describe in a little bit more in detail on one example on a time series analysis. This work is a joint work with three of my students, Vanessa, Veronica, and Federico, and a colleague of mine, Gabriele Arnulfo, and Dr. Lino Nobili, who's the clinician who's helping us trying to devise the significance of our result in the epilepsy domain. Before digging into the details of the example on the epilepsy and the time series analysis, I'd like to discuss a little bit more how what are the issues of inferring models from biomedical large-scale data. So this is a word I hate personally. it's more like if you're dealing with data in biomedical and in the biomedical domain, it's not. It's rarely big. Usually it's mostly it's large scale, meaning the paradigm of large P, small n, lots of dimensions, small, few samples. So it's really not big usually, except with the exception of all the imaging that's coming from the biomedical domain. But it's growing. So this is a paper from 2015, so it's fairly old now. It's 3 years old, and we know that it's going to grow big. So the data from the biomedical domain is becoming really big. So it's the projection is that in a few years, it's like 7 years from now, we expect to have genomics data really doubling the the amount of data coming from the social media. So we know that we have to be prepared in understanding and having tools that allow us to deal with large scale, with big data in the biomedical domain. As data scientists, we have to be careful, not just minding the methods or the management of the data, but also trying to talk to the domain experts, like doctors, clinicians, and so forth, in order to really understand what they are expecting from us. So it's really an interdisciplinary domain, and we are aiming at, we are trying to develop a common language with doctors and clinicians in order to really understand what they expect. What I'll try to discuss also is it's actually the most new, the newest part of our research, which is the visualization of results, which is very important for clinicians in order to understand what we did on the statistical viewpoint and trying to convey the importance of our results also to them. Regarding the time series analysis, well, one comment I'd like to make is now it's really easy. It's easier than ever to gather data over time. One example is really the data coming from wearable devices. It's really overflowing. It's coming. It's really easy to collect, and it may give us opportunity to understand complex phenomena. Not just wearable devices, let's think about genomics over time or molecular data over time. This is having data over time may allow us to understand complex phenomena also happening in the human cells, and therefore understanding complex diseases such as tumor or neurodegenerative diseases. Therefore, it's really important to being able to understand the information conveyed over in time series data, and it's growing. The interest towards this kind of data is growing from science, from the research viewpoint, and also from industry viewpoint. We are working mainly, we are all here because we think that Python is a very powerful tool to deal with data in general. And therefore, I won't go too much into details of our code. I'll pinpoint where the code is available. But mainly, we rely on Python for dealing with data, with the structured data. Obviously, as machine learning people, we are basically doing linear algebra all the time. Therefore, we take advantage of all the tools that Python is giving us. I really don't believe in reinventing stuff that's already there. So obviously, NumPy, SciPy, all the tools for signal processing, especially in time series, it's very important to being able to deal with to pre-process signals and extract features or discard what we don't want to have. I'll mention the fact that, for example, one other very convenient thing is we also take advantage of Python as in the flexibility of being able to connect with other external libraries. It happened especially in this project once. And this is our favorite part, as we work with scikit-learn, obviously, and also we implement the algorithm on our own. So we rely also on, especially for the deep learning part, on TensorFlow Keras. And this is my new favorite thing. We are trying also, as I said before, to visualize the results, and we are leveraging on the power of the visualization libraries. Okay, so these are sort of our favorite tools. What do data actually look like? So I would say we are spending most of our time preparing the data. So that's frustrating most of the time. I would like to dig into methods and results and see how it's going, like the algorithm, how they are doing, and so on and so forth. But actually, data scientists are really spending lots of time in preparing the data. And as data are really messy. So we were trying to answer to very fancy questions, especially from the clinician viewpoint. But really, what we are doing half of the time, I would say, is trying to sort out the mess in the data. Data are messy, so data have tabular usually, most of the time, they are tabular formats. They don't have a standard. They are gathered from different people with different criteria. And so really one of the challenges, I would say, as a data scientist now is really data are really messy, and therefore one advantage of having tools like, for example, pandas, being able to sort of import data in any form is really an advantage, because it's really what we do most of the time. Data preparation is really one thing especially in the biomedical domain, is really crucial, and it's a challenge, and there are really the interoperability of data is really not there yet. Not even when doctors are using software, like dedicated software, like say electronic health records. There are already bunch of different EHR softwares for allow doctors and clinicians to store information in a structured way, but then still it's really not there's no such thing as one standard. So for everybody that lives as a data scientist that aims at understanding what's going on in a given disease, one great challenge is, how do I gather data, collect different data, and how do I, for example, deal with data coming from different hospitals? So this is one thing that I would like to point out. Having tools that allow to deal with different data structures is really important. Okay, so what we did is, the first thing you do as a data scientist when someone is coming to you asking one question in the clinical domain is, okay, I'd like to really have sort of an idea of what's going on, not really. It's the first part is really data exploration. So it's not, I'll think of the best algorithm to solve your problem, but rather is there really a signal behind the question you're asking me? So the first part, one of the first attempts for us was to sort of build this tool that allowed us to perform a data exploration. And so we did this sort of with this simple library, which is integrating all the steps that one is tends to do as a first step in understanding the content of one data set. So exploratory data analysis is really providing us some tools to getting insights on a data set and possibly uncover underlying structures. In particular, we were thinking of dealing with genomic data, which are usually very high dimensional. Therefore, we wanted to be able to analyze data, large-scale data. And the other part was we wanted to minimize the effort in providing clinicians with some sort of tools in order to visualize what was going on. Okay, so these were the three goals of this small project, and therefore we thought of what are the steps that we do as in the exploration pipeline, data exploration pipeline. We have data in any tabular form. Usually it's really a tabular form of some sort. What we do is sometimes data are missing, so we have missing values because the measure went wrong or because someone forgot to write down something, and so on and so forth. So the first step is usually, what do I do with missing values? Do I discard the entire sample, or do I try to sort of fill in the blanks and input missing values? Well, most of the time, as we are working in biomedical domain, we don't want to discard any sample because each sample is really precious. Each sample is time consuming in the gathering and is usually also costly. So missing values are really an issue. We'd like to be able to impute the missing values. So given the data set we're dealing with, we decide which is the best imputing criterion. Then we have some sort of preprocessing. So do we keep the data as it is? Is it raw? Is it homogeneous from the viewpoint of which measure we are using? Or is it a mixture of different measures? Say we think about data from patients. It could be questionnaires, so it could be categorical. It could be a measure of some sort of the height, the weight, blood pressure, whatever, or it could be also some sort of genomic measure. So data may be really heterogeneous, and therefore preprocessing helps us to sort of standardize and normalize the data, and therefore being able to use the optimal machine learning algorithms afterwards. So which is the best preprocessing step? Well, we have different criteria. We could choose different things, different algorithms to proceed. And usually these are all sort of parameters in the pipeline that we are building. So we have different choices for the missing values imputing, different choices for the preprocessing. Then the goal of the exploratory data analysis is, are we seeing something in the data? Are there patterns in the data? Well, usually one proceeds with some sort of clustering, dimensionality reduction, so on and so forth. And here again, we have different choices. And lastly, we'd like to see if, without having any information, without using explicitly any supervised information, labels, so on and so forth, we proceed with some sort of clustering. So the idea of the adenine was, okay, I'd like to see what are my options in terms of what are the best. All 4 steps are usually an arbitrary choice of a set of algorithms. So why don't we do them all? It's really a data exploratory analysis. I'm not going to say anything conclusive yet, but then I'd like to see if there are patterns in the data. And what we did is, okay, we tried to sort of set a pipeline which is able to incorporate all different algorithms in all different steps, relying on standard tools from Python. And what we did is really provide us with a simple tool that gives us all the options. So it's really a command line tool that you can actually tweak with a choice from the inputting algorithms, set of different preprocessing algorithms, different dimensionality reduction algorithms, and so on and so forth. So it's sort of a 4-dimensional tabular results of all the possible combinations, all the algorithms, and all the clustering things. The other advantage was for us being able to go back to the doctors and say, okay, we ran a data exploratory analysis. There was a preliminary analysis, and we're able to convey some sort of visualization. The other advantage for us was we implemented everything in order to be able to run it on a single machine and on a distributed facility. So it's really basic, but that's what we wanted to achieve. So the results are really stored sort of in a hierarchical set of folders. And the visualization part, I'm going to show you here briefly a little example on genomic data. So we just considered data set of colorectal cancer. So it's a really sort of usual classic binary classification problem where we have patients and we have control tissues. And then we have genomic data. So the data is molecular. We have about 35,000 variables for each patient and for each control. So all in all is about 360 samples. So that's the dimensionality in the sample and the 35,000 dimensions. The goals may be, okay, how do I visualize the cancer versus control samples? It's really unfair from the machine learning viewpoint. We are projecting something that usually lives in such a high-dimensional domain onto a three-dimensional domain. But then that's something that's really useful usually for getting really starting to discuss with doctors. And so it's really something that one tends to do anyway. The other goal was, okay, how do I infer if there's such a structure, a correlation structure between among the variables? So these were the two goals. And this is an example of a result from adenine. Well, are we happy? Well, we are fairly happy with this visualization. Okay, we see that there's some sort of discrimination between the two classes. And this is one possible combination of preprocessing, data dimensionality reduction, and clustering. The other one is a visualization on the two classes. So we have the control samples and the patient samples, which are different. And so the question is, do we see a difference in the structure among the variables? And therefore, this is an easy tool to sort of visually inspect if there's something going on. Okay, this is not exactly what we do. So that the goal of a data scientist is to make sense of data. So it's more than a exploratory data analysis. So how do we make sense of data? Well, now it's really, artificial intelligence has become again a popular term. And under the umbrella of artificial intelligence live many different sort of subdisciplines, I would say. And I would focus mainly on what I've been doing in the past 10, 15 years, so machine learning. And actually, I would mention, I would sort of focus on a very specific subtopic of machine learning, which is regularization methods. But before going into that, most of you already know, I expect most of you are already familiar with machine learning, but this is a very, I think, beautiful definition of what machine learning is. So the goal is to being able to program something, to predict something without explicitly programming. So the giving computers the ability of taking decisions without considering all the options, I would say. So it's really something that differs from data mining, because instead of looking for hidden patterns, I'm trying to building models that are statistically significant and also are able to predict how sort of the future, so unseen data. I'm able to sort of decide what's going on, what will go on unseen data. So it sounds fantastic, but it's really just a pile of linear algebra most of the time. So basically, it's really a mixture of different optimization methods relying heavily on linear algebra. And that's just it. So usually it's really also in the deep learning, I would sort of pinpoint deep learning, but then we are trying to solve, to obtain a model which is predictive and also possibly interpretable, especially in the biomedical domain. What we want to do is obtaining statistical model which is able to predict, but that it can be also explained to the clinicians. Usually, clinicians are already able to predict what's going on with a patient. They are already able to say, oh, this one is going to respond to such drugs and this one is not. Or this one is stage 1, this one is stage 4, so on and so forth. They have clinical values or clinical parameters that usually help them to sort of know what's going on and what will go on. But what they don't know is why is this happening, for example, from the molecular viewpoint? Why the genes of this person are sort of driving him to being healthy at some point, and this one is instead going bad. So the big question from their viewpoint is help. They ask for help to data scientists in order for understanding better what's going on at a different level than the clinical level. So the other, where are we using heavily linear algebra? Well, the other one is usually, as I said before, we are living in a scenario where we have few samples and lots of variables. Therefore, especially when using machine learning methods, regularization methods, we are living with the fact that we have to choose parameters, and I'll explain why in a second. And choosing parameters usually relies on cross-validation methods, resampling methods, so on and so forth. And therefore, being able to computing stuff fast and possibly on high performance or distributed facilities is key to being able to also obtain results that are statistically significant and robust. Okay, so the first few minutes I'm gonna discuss the old-fashioned method. So machine learning as we knew it until 3 years ago, maybe 4 years ago, 5, I would say, which relies on 2 steps. I have signals, I have data. It can be a one-dimensional data, one-dimensional signal, could be images, could be genomic data, whatever. And what I do as a machine learning person is one step of feature extraction. I describe my sample in a different way with respect to the input data. So I have been given a set of measures. This set of measures characterize one sample, and then I extract some features out of it. And this feature extraction process is sort of really driven from the domain viewpoint. So if I'm dealing with images, I know that possibly I'm going to extract corners or edges or color histograms, so on and so forth. If I'm dealing with molecular data, I'm going to extract something else. And this is possibly driven with the help of, guided with the help of clinicians. And then the second part is whenever I've reached something which is a data matrix, I'm going to proceed with the machine learning step. So this is a paradigm that didn't change even when machine learning evolved towards, for example, deep learning. We have sets of examples. Let's consider one-dimensional data, and it could be anything. Let's consider a simple one. It could be audio files, so these are different kind of musics. And I have a function which changes, it's a time series, changes over time. And really this is, ideally this is the sound over time. How does it change over time? What I'd like to do is being able to, for example, model this different kind of music into a classifier that is able to distinguish rock from jazz, for example. So I'll proceed with, as I said before, extracting features from the the time series, and then building a model, which is sort of which is able to, given any given any example from the data set or new sample, is able to assign this new sample to the classes that I've considered before. Well, how do I do that? There are plenty of options, obviously. So if I'm dealing with one-dimensional signals, the idea is always, how do I sort of represent my signal, being it a simple one or a complex one, into, for example, a linear combination of simpler signals. So that's the idea of the Fourier theory. So the blue line can be represented as a sum of a linear combination of the two green lines, okay? And then the information, the amount of information that I had in the blue line is really exactly stored in the combination of the two on the two green lines. It's really this idea that helps us representing complex data in the time. Let me see if this works. Okay, so I have a function over time. It's a signal over time, and I know that I can actually represent it as a sum, as a linear combination of sines and cosines. This is the idea behind the Fourier series. What I could also do, sorry, it got stuck, okay, is how do I, being able to represent the signal as a sum of sine and cosines also allowed me to keep in mind that the sine and cosine is defined by its frequency. So instead of keeping the representation of the input data as a series of amplitudes over time, I could just keep in mind the coefficients of the sines and cosines that sort of approximate the red line in the frequency domain. Okay, so this is very convenient because instead of keeping possibly a very large amount of data, I am just sort of obtaining a compact representation, which is just the sets of coefficients that I need to approximate my input signal. So the information is represented as an array of values, obviously, and this is sort of giving me the advantage of representing any signal in the same way, and giving me also the possibility of comparing and building measures over the same representation. The dimension of the signal is defined by the amount of coefficients that I'm keeping. Okay, so the goodness of the approximation that I'm sort of designing to keep. Okay, so what's the next step? Fisher extraction has allowed me to sort of represent all the data in the same way. So I have a bunch of examples, and possibly I have a label vector. That could be the genre of the music that I'm considering. As I said in the example before, I have rock music, I have classic music, and so on and so forth. And one possibility is, okay, how do I decide which is which? Well, the usual representation is I have data. They live in a multivariate world. Obviously, to drawing stuff, I have to sort of simplify it in two-dimensional plane. And the goal is to possibly devise a criterion that classifies one class to the other. The other possibility, classic possibility, is okay, in the supervised setting, I have the same set of examples, and I have ratings. This, for example, that could be the ratings of my music on Spotify. So instead of having a classification problem, I would have a continuous set of variables that are my labels, and therefore I want to sort of be able to approximate a function which is a continuous function in the output domain. And therefore, that's the other sort of great prototypical problem in machine learning, in supervised learning, classification or regression. Okay. Whenever learning from data, either I have the possibility of having Google Images, so a very large amount of data to learn from, but especially in the biomedical domain, this is not happening most of the time. So I have few data. So how do I deal with the fact that I'm gonna by definition, I'm gonna allow some error. Do I accept errors on the training data? Yes or no? Well, for example, we have to keep in mind that if we aim at producing and obtaining the perfect classifier on the training set, there's a high chance that when I'm gonna try it on different data on the test set, this is gonna be not exactly what I'd like to have. So the generalization issue is some issue that either I sort of overcome with having lots of data, or I overcome with having methods that are keeping in consideration the fact that we are sort of living in a noisy world. So regularization is really that simple idea that combines being able to provide a data term. So the regularization, all regularization methods are really measuring the function. So this f is the predictor, is the classifier or the predictor function. Y is the label vector. We have we decide a loss function, which is measuring how good I am, how good the function is on the input data, and there's this discrepancy between the two. And the other part is usually a penalty term, so a regularization term. This term is sort of governing the complexity of the function that I'm looking for. Am I looking for just a linear function or a polynomial function or so on and so forth? So this is sort of helping me keeping it simple. And the other really crucial part is, okay, how do I what's the trade-off between the two parts, okay? And this is the parameter of, that's called the regularization parameter. It could be just one or more than one parameters. And usually these are parameters that have to be chosen according to the data we have. So there's no such thing as a magic number. We have to choose this lambda, these parameter or parameters according to the data I have. Some comments on the fact that the loss function and the regularization penalty may have different functional forms, and therefore, from the algorithmic and optimization viewpoint, as I'm looking for, this is a problem of looking for the minimum between sum of two things. So depending on which loss function I choose or penalty term I choose, it could be a nightmare to obtain, to have guarantees on the fact that there's such things as a minimum exists or not. The other part is, especially when dealing with many variables, as in the biomedical domain, R is usually containing a term that requires the sparsity of the solution. And as I said before, the parameters, the regularization parameter, have to be chosen according to the data we have. A little step forward. Well, usually, I mean, the modern approach to it is not, let's keep the feature selection, the feature extraction part, and let's learn the representation directly from the data. So more advanced methods, including our favorite new thing, I think, the deep learning, are aiming at solving both steps at the same time. So instead of engineering the first part, so the feature selection part, they aim at finding the best representation that conveys the best prediction model. It's really, there are plenty of pros, flexibility, scalability, especially if we think of deep learning, learning power, and so on and so forth. One con could be they are not exactly easy to interpret. So if interpretability is a key for clinicians, that may be a problem. So what I'll describe as in the example in the next few minutes is we opted for a method which is sort of keeping and trying to maintain the interpretability. Okay, so let's begin in the example I wanted to discuss. This is a funded work from Compagnia di San Paolo. And the goal is understanding focal epilepsy. So we have epileptic patients. Focal epileptic patients are usually treated with drugs, and if they don't respond well to drug, the only option for them is undergoing surgery. So it's a very invasive procedure, obviously, because they have to, so the doctors and surgeons have to sort of open and cut out the part of the brain that is causing the epilepsy attacks. So that's called ablation, and it's really, really the last thing that they want to do on a patient. So if it's really a solution that's considered only for pharmacoresistant persons. The other part is for clinicians, is for neurologists, is before undergoing surgery, patients have to, and actually doctors have to really locate where exactly the part of the brain is that's causing the seizures. And therefore, there are several ways to sort of measure the electrical activity of the brain. And the stereoelectroencephalography, which is the measure that we are using, is the most precise one, but also very invasive, because they have to sort of implant electrodes in the brain, and the patients have to stay with this sort of implanted thing for a few days. They have to be hospitalized and so on and so forth. And from the doctor viewpoint, the time series that are collected are very hard to analyze. Usually they have to spend lots of time sort of visually inspecting all the data in order to understand where are the channels that are really close to the epileptogenic zone. It's time consuming, and also, as everything in medicine is really subjective. So usually more than one doctor inspects the same data in order to be sure. So the data we are dealing with so far luckily is the data set is growing as the project proceeds, is 65 patients. We have data that are collected in between seizures. So far we don't have the opportunity to have time series collected when the seizure occurs. The sampling frequency is 1 kilohertz, and we have about 15 electrodes per patient implanted, and about 150 channels per patient. So the idea is that we have these electrodes that are implanted, and then for each electrode we have sort of a different spot where the electrical activity is recorded. So these are called electrodes, and each sort of short line is called a channel because it records a different part of the brain. So the amount of time that we are recording is 10 minutes at 1 kilohertz. So the time series all in all is about 600,000 points in time. And this is one example which is fairly easy to understand. It's usually the data are really the time series are really very noisy. This is really one easy visualization from it could be read also by someone who's not familiar with, but usually it's really not that simple. So we have different for each channel we have different electrical activity. What we are aiming at is to characterize which channels are pathological and which are not. So imagine having a three-dimensional sort of semisphere. We have channels, electrodes implanted in it, and we want to be able to say, okay, this channel is really epileptogenic, this other is not. Because then we know where the channels are located in the brain, and therefore we are able to sort of identify which is the epileptogenic zone. The idea is we want to be able to sort of produce an automatic way, and so the doctors are still very much needed, but then it could be a support system for them in order to help them visualize easily which are the suspects, so which are the channels that are most likely to be epileptogenic. So the prediction of which channels are sort of bad, and also possibly would like to be able to provide the clinicians with a visualization system that helps them seeing the characteristics of each patient in a convenient way. The other interesting question, it's actually the question I like most, is a signal as a signal in the brain is really a combination, a superimposition of different signals. So which are the most discriminative frequency bands are really characterizing the physiological and healthy channels with respect to the pathological channels. So we expect, from the literature, we know that spike and waves, there are some peculiar waveforms that are characterizing pathological channels. One is, as I said, spike and wave, which corresponds to a very sharp change in the voltage in a short time, and then some sort of reaction and different waveform that happens after. And the other one is HFO, so it's high frequency oscillations. So we expect to have some sort of frequency bands, especially in the high frequency domain, which are characterizing the behavior of pathological channels. And so we want to verify this. What we resort to is a multitask multiple kernel learning method, which is sort of based on the regularization. It's in the family of the regularization methods. And this is sort of the pipeline that we are implementing. So we have a time series, we have channels per patient and a set of patients. So we have P is indicating the number of patients we are dealing with. And actually the results I show you now were measured and were obtained analyzing just a subset of the 65 patients, because the 65 patients is really fresh new. The results are coming from a third of them, mostly, like 20 patients. As I said before, we had to resort to preprocessing, simply because we are dealing with electrical signals, so we want to discard some kind of constants that are affecting the signal. And then we resort to multi-scale analysis. So first we undergo like some sort of cleaning of the signal. Then we transform the data using wavelet transform. So I'm not going to comment on the details. So I'm just, it's a way to sort of represent the data both in time and frequency. And then we build for each data, we build 3 different kernel types. Kernels are functions that are sort of measuring the similarity between data. And then we proceed with the multitask multiple kernel learning. Okay, so I'm going to briefly describe what we do in each step. So the first part is pre-processing of stereo electroencephalography data. As I said, we have raw signals in the temporal domain. We are basically heavily using any kind of tool that Python is providing with us. So we filter out constants and power line effects, the 50 hertz. That's affecting the measure by definition. And we obtain the preprocessed signal. So we switch from the time domain to the frequency domain, butterworth filter, and then we obtain a sort of a filtered signal, which is still raw, but without artifacts. All the artifacts we know about, actually. And then, as I said before, we have the multi-scale analysis. I'm just giving you the idea of what wavelet transforms are allowed to do. So this is the input. From the previous step, we had the preprocessed signal without artifacts, okay? And what we do is we have wavelet theory allows us to choose different mother wavelets. Let's think about them as a filter. And what we do is we filter the original signal with this mother wavelet at different scales. So considering different the idea is considering different time intervals. And what we obtain is a time frequency representation, which tells us which is the most, the frequency that are most important to characterize and approximate the signal. So it's really a way to, as the Fourier theory, the example from the Fourier theory before, we are sort of approximating, trying to find a different representation of the signal that also gives us an insight of which are the most characterizing domain frequency bands. So the representation of each channel is now something which is not a one-dimensional signal anymore. It's sort of a matrix. On this side, we have time. So again, we have sort of about 600,000 time points. And here we have scales. So sort of the frequency bands idea. So each channel has now become something a little bit more complex. And a comment here. The wavelet library in MATLAB is pretty popular because I think for historical reasons. So if you ask someone, okay, which wavelet library do I use? Well, MATLAB is really one answer that comes often. And therefore, if you want to use the wavelet library in MATLAB, there's no problem. Let's import it from the APIs as a Python package. So this is one thing that we had to do at some point because one of our colleagues suggested us, okay, let's use that library because it's really the one that I've been using forever, so on and so forth, and that's without switching to MATLAB, that's what we did. So he was happy. And okay, after that, so now we have filtered out stuff, filtered out all the artifacts, and we have a new representation of the data. So this is sort of the feature extraction part. But then we want to sort of learn to characterize. So the aim is, am I going to be able to sort of predict which channel is pathogenic and which channel is not? We resort to kernel methods. So the idea of a kernel is really mapping something into some input data into some other space and measuring the distance. So it's really, the idea is I measure distance between input points, okay? And I can actually define different kernels, enhancing or depressing some characteristics of the signal. The easiest example of kernel is the Euclidean distance, but then I could use a correlation of different different ways. There are obviously different options to define kernels. Gaussian kernel is actually most popular. Here we decided to combine 3 different kernels. Actually, I don't know why I picked up an example with 4, but then we are using 3. We have, so for each kernel, we can define a matrix, which is, whose dimension is n by n, so the number of patients times the number of patients, for example. And then I could combine the kernels with different parameters. So if I want to sort of use different measures that are sort of enhancing different aspects of the signal, I could do that. But one new parameter that I have to learn is how do I weight these parameters. It's a linear combination. I want to sort of find which is the best linear combination to discriminate pathological channels from healthy channels. So I use different measures and then have to sort of learn also which is the best linear combination. So boiling it down to one problem, well, we chose to use different measures, all driven from or imported from the signal processing domain. So we used the correlation, the cross-correlation, phase locking value. That are measures to sort of measure that compare different signals. So for each patient, we perform a pairwise comparison at each scale. And therefore, we use 3 different measures, 3 different kernels. So we have 3 kernels per each scale. As we had 100 scales per channel. Therefore, we have 300 kernels, 300 kernel matrices, whose dimension is the number of channels times the number of channels. Okay, so one patient is a set of CP channels. Each channel is 100 times 600,000, and I perform a kernel comparison. Therefore, for each scale, I obtain a value that's comparing that by using the kernel that's comparing the two arrays for each scale. So all in all, the predictive model I'm looking for is a linear combination. These are known parameters, so these are part of the problem. It's a linear combination of kernels, again, and then we are expecting it to be weighted, so the regression coefficients, alphas, again, unknown. And we learn 1 model per patient. So that's why it's multitask. Each patient is a different task. We couldn't gather all channels together because patients are measured in different places. So we expect the epileptogenic zone to be possibly in really different areas of the brain for each patient. So we couldn't say, okay, let's gather all the channels together and just perform a binary classification task. That wasn't feasible because it's really not the option because each patient is different. So we had to perform a multitask problem, and for each patient we sort of find the best predictive model. The advantage of keeping them together is we sort of request some sort of we sort of try to incorporate some characteristic into the model from one patient to the other. So the functional looks like this. It seems nasty. It's not. The loss function is a logistic function, a logistic regression function. And then we have 2 terms. So the regression part, as I said before, you could recognize the data fit term, which is governed by the logistic function. And then we have a part which is the regularization, the 2 penalties actually. One penalization term works on the regression coefficients alphas, which are these guys here. And the other one works on the kernel weights. So the two regularization terms are really helping us understanding which is the best combination of the kernels and which is the best combination of the regression coefficients. Okay, so for each channel we have a label. So the doctor said and assigned a label to each channel. So this is a supervised setting. So this array here is telling me this channel is epileptogenic, the other one is not. So it's really a binary classification problem. So far, we want to perform a little different experimental design in the future, but then we kept it fairly simple. So we are still not able to sort of validate and obtain one model. So the results that I'm showing you are results from the validation in a cross-validation setting. We actually shuffle split the data sets 50 times, and keeping half of the data for model selection and learning the model, and the other half for validating. Okay, I think I have, how much time do I have? Another 5 minutes, okay? Okay. I'd like to comment what we obtained. So the first part is we sort of ranked the weights of the kernels. And as I said before, we are working multi-scale. So we have kernels and frequency bands. So we are sort of able to rank which are the most relevant, the most used bands overall, the entire data set of patients. So this result is on all patients. What we are observing, which was the part where we were happy to see, is that most of these frequency bands live in a high frequency domain, which was what the clinicians were expecting. So we have sort of the most important, the most relevant bands were assigned to the phase locking value and amplitude correlation. So 2 of the 3 kernels. And the kernel weights, the most important frequency bands are actually living in the high frequency domain. The part of the spectrum that they called high frequency oscillation spectrum. So exactly what they were hoping for. This is the same result in a table format. And if we go and analyze one patient at a time, because really one patient is different from the other, so we are sort of, we can actually observe what's going on also patient by patient. We observe that this is the alpha weight, so these are the regression parameter, the regression coefficients. And so we see that for each channel, we can actually see the difference and the weights that are sort of assigned to the critical channels and non-critical channels, so the pathological channels and the healthy channels. Okay. Again, this is what happens in training, so on the training chunk of the data set. And that's what happens in validation. What we do is we are using logistic regression, so we can actually interpret, we can attempt to interpret the value of f of x as a probability. So what we are showing here is for each patient, as we are sort of repeating the experiment 50 times, this is the average and standard deviation of the probability value assigned to each channel for one patient. So what we observe is, aside some exception, we see that the clinical channel, the predictor is sort of working fairly good because it's the value here, the values for the critical channels are fairly high. So that means that the prediction function is assigning higher probability of being critical to the actually critical channels. Okay. And to conclude, the model performance on all patients, these are a set of standard measures, the balance accuracy, F1 score, prediction recall, and so on and so forth, on all patients. So again, the results are so far fairly encouraging in terms of what we are obtaining in being able to predict the pathological channel versus the healthy channels. One last bit, and I'm done, promise, is what we are doing right now, so the visualization part. As I said before, one other goal of our project is to provide the doctors with some tools that are actually enabling them to visualize in a more automatic way the signals. So it's basically we're starting, this is a very, we are sort of working with standard tools, but very powerful, the Jupyter Notebook, generating HTML pages, so they can actually use a browser from wherever they are. Visualizing the time series and using Bokeh, we are sort of giving them all sort of simple tools to using thresholds. They are used to really play with the data a little bit and sort of clean them manually using setting thresholds that they feel they're right. So what we are doing right now is really starting to work towards building a visual inspection tool that also possibly will combine the results from our predictive model. My last slide is to thank my group, which is sort of what they are mostly doing all the work. And all the code is available either at the GitHub personal pages or our group GitHub page. Okay, thank you all for your patience. Thanks.
Question?
Thank you for the talk. I was just wondering if what was you saying about high frequency channels? Mm-hmm. What I was thinking is in your data that you passes to the last step of machine learning in that case, there are actually a lot of data that comes from that favorite thing, and most of them are high frequency. So how do you make sure that the effect predicted by clinicians are not coming from there? Like you have lots of data in high frequency domain and only small amount of data in low frequency.
High frequency is characterizing both in a different way the pathological channels and the physiological channels as well. So I wouldn't say that physiological channels or the healthy part is just low frequency. It's really the different amount of high frequencies that occurs in the two classes that really makes the difference. Also, what we saw is that high frequency play a role, but still doctors are unsure that that's the only part that plays a role. So what we are aiming now is we'd like to increment and use other kernels in order to emphasize other aspects of the signal and see. So we chose 3 different kernels now. We'd like to use maybe another 5 in order to sort of measure and similarities in other kind of different bands, frequency bands, and see if this is sort of changing what we see as a result from the interpretation viewpoint, so from which band is most important and most relevant. But I wouldn't say that healthy channels have just low frequency parts. This is not the case actually. So the amplitude doesn't have any. So what I showed you, it was like a very easy. So sorry. So this kind of signal here. Well, it's the fact that these channels have more amplitude doesn't have anything to do with the fact that they also have a higher frequency, most relevant high frequency component. So we also have high frequency phenomena in the healthy channels.
But the thing is,
I have
Sorry?
But the thing is, you have much more data in high frequency anyway, because wavelet analysis gives you much more.
Yeah, but that's why I'm doing multi-scale. So I'm trying to sort of not deprecate just the or emphasize only what I'm looking for. We were sort of agnostic on the front of which frequency band is the most relevant. That's why we wanted to stay multi-scale, because we wanted to keep most of the information. We want to retain information we need. So it's, sorry.
I'm not sure if you have commented on it, but I have two quick questions. Like, one is the data available, or will it be? And then the second question is about the ground truth. It's the ground truth like that the doctors say, okay, this is the channel, or is it that you have actually take out part of the brain that was corresponding to that channel?
That's great. Both great questions. I'm not sure yet if our data will be available, but there's actually one very good data set we found that we're actually using. It was a Kaggle competition a few years ago, and it's open and it's well annotated. So there are some kind of similar data sets available online. I hope we will make it available, but I'm not sure yet, not until the project is done, so in another year, possibly. The other part is ground truth. I agree with you. It's really right now we are trusting the clinician we are dealing with and his team, mostly. So it's really what we'd like to use also is, for example, prior knowledge on the structure of the brain, which may help us understand if the labels that we are, because now we're really using just the labels that they give us. We have some measures of connectivity, so the connectivity sort of gives you an insight of which channel is connected to which other channel, not because they are close to each other, but because the brain is sort of connecting them. And this is something that I'd like to use in the next future to sort of see if what we see is really does really make sense. Also because the structure of the brain connects them, for example. So I agree, the ground truth is really one shaky part. So right now we are sort of just trusting what we have in terms of the expertise of the domain expert we are dealing with.
Thank you for the talk. I was wondering, how did you evaluate the validity of your pre-processing steps in order to ascertain that you are not losing any frequencies during the filtering? Right.
Yeah, we just kept it as simple as possible. So just discarding the 50 hertz and some basic effects. So stereoelectroencephalography is a fairly standard procedure. So whomever is taking the measures, is acquiring the measures, is sort of knowing what may go on in the acquisition phase. So we just use those information plus the 50 hertz. And that's the only thing so the pre-processing is fairly just a filtering process, very standard, nothing fancy, because we really didn't want to discard any possible information.
Thank you.
No problem.
Thank you for your talk. I have a question about sort of how you interact with your group, because you have a very large project that spans a number of different areas, and you also have a very large group. how did you ensure that new members to your lab got up to date with what you'd already done? And conversely, if people left, how did you make sure that that knowledge didn't go with them, basically?
That's a very good question. It happened recently, actually. I've been doing machine learning a few years now, and what happened is that, especially for the basic things like being familiar with cross-validation, or being familiar with what's a test set, what's a validation set, and these are, these are sort of the ABC of anything in machine learning. And then I tend to forget that the new people coming into the group, even if they had some machine learning in classes, it's not a given fact that they are able to sort of dig into the data analysis. So being able to understand the algorithms is one thing, then when you get into dig into data, it's a very different thing. And it happened a few times that we had some sort of panic moments in the group because someone didn't really get what was the difference between validation and test, and everything went, a little bit nuts for a few hours. Then we were back on track. So, well, I learned over the years. What I do is now we are trying to sort of keep everything on GitHub. So the code is there. Share the code is one rule. We tend to work in groups. So there's one person in charge of each sub-project, but there's also someone else sort of either collaborating or supervising, mostly collaborating, so it's really like groups. So this work was mainly driven by Vanessa, Veronica, and Federico, which were sort of sharing the three parts. So Federico was mostly on the implementation of the algorithms. Vanessa was driving the entire process. Veronica, some other part. So it was like, it's really subgroups of people trying to sort of teaching each other their own expertise. And and like senior, the senior members are sort of trying to keep in mind that cross-validation is a thing that they may not know, and so on and so forth. So I think it's really challenging, as you said. Mostly the code, using each other's code, for example, is one great advantage. So you sort of validate the code as well and learn new things. So.
Okay, unfortunately we have no more time for questions, so thank you very much, Annalisa.
Thanks for being here.
Okay, so raffle time. So give me 2 minutes and we will start with the raffle. I will kindly ask the people in the other room if they can join us here just for this, and then we have the coffee break. ready to go. So, these are the data. Basically, I got these conference participant stuff. Actually, we have 191 eligible. I just got the names of participants in the conference. So those buy the ticket for the conference or both tutorials and conference, of course. So these are that we have. I just merge first name and surname, and basically assure that the same names will stay in. Okay, so, and this is the price. 5 copies of for free of this book, Data Science Scale, with Python and Dusk, kindly offered by Manning Publishing, one of our sponsors. Okay, so let's go for the first one. Live. Dimitri, is he here? No one? Okay, next one. Christian. Shame on you. Phil? Guys, come on. Finally. So you got your discount code. You're welcome. All right. Let's go for the second one. Declan? Oh, you guys home? Another Christian? Finally. Christina. Thank you. It's also handily written, so it's precious, more precious, valuable. Let's go for the third one. Alexis. Okay, we have. Two left. Ronan. Let's go. And so the last one. All right. Okay, thank you very much. Enjoy the coffee break. Quick announcement for those meaning to do the lightning talks. Please make sure that your laptop will work with this system. Okay, so try to test it during the coffee break or lunchtime. Okay, thank you very much. Guys, sorry. Sorry, I forgot another thing. We found a copybook, a workbook here in this room, a black one, black cover, okay? So in case you missed it, we have in the registration desk room, okay? We'll send you a photo of it on Telegram.